Something just happened to Earth's oceans that scientists were not expecting to see this time of year. The global average temperature of the world's oceans has reached a new record, and the timing may be just as important as the number itself. On August 22nd, the average sea surface temperature across the world's ocean outside the polar regions reached approximately 21.1 degrees Celsius. That is the highest daily value recorded in the modern Copernicus dataset. The previous record was 21.9 degrees Celsius, set in March 2024. The difference between those numbers is tiny, just a few hundredths of a degree. But the timing is not tiny at all, because ocean temperatures normally reach their global maximum around March and April. By August, the world's oceans have normally already passed their seasonal peak. Instead, temperatures have continued climbing, and now the ocean has crossed a record that was only set during another exceptionally warm period. So the obvious question is not simply, how hot is the ocean? The bigger question is, why is it this hot now? And what happens if this heat continues building? To understand that, we have to look beneath the surface. Because the ocean is not just a giant layer of water sitting beneath the atmosphere, it is Earth's largest heat reservoir. The ocean absorbs enormous amounts of energy, and when that energy changes, the effects do not necessarily remain at sea. They can spread into the atmosphere, they can influence storms, they can change rainfall, they can raise sea levels, and they can put enormous pressure on marine ecosystems. That is what makes this latest record so important. It is not just a number on a temperature chart. It is a measurement of energy inside one of the largest systems on Earth. And right now, that system is unusually warm. There's another detail that makes the current situation even more interesting. This is happening at the same time that El Nino is strengthening. El Nino is a natural climate pattern involving changes in the tropical Pacific Ocean and atmosphere. During an El Nino event, unusually warm water develops across parts of the central and eastern tropical Pacific. That warm water changes rainfall and atmospheric circulation. And because the Pacific is enormous, those changes can influence weather patterns far beyond the region where they begin. The current El Nino is adding heat to an ocean that was already experiencing long-term warming. That distinction matters. El Nino did not create the long-term warming trend. It is a natural climate pattern occurring on top of a warmer baseline. Think of it like this. Imagine a room that has been gradually getting warmer for years. Then someone turns up the heater for a while. The heater did not create the underlying trend, but it pushes the temperature even higher. That is roughly what scientists are watching in the ocean right now. The long-term background is warming. Then El Nino adds another pulse of heat to the system, and the result is an ocean reaching extraordinary temperatures. The Copernicus data is especially interesting because this is not based on a single thermometer floating somewhere in the Pacific. The estimate combines observations from satellites, ships, and buoys with sophisticated ocean and atmospheric models. Copernicus uses its ERA5 system to reconstruct conditions across the planet. A separate Copernicus marine system also tracks the ocean independently, and both systems have been seeing the same broad signal. The ocean is exceptionally warm. That independent agreement is important, because when different observation systems point toward the same result, scientists can have greater confidence that they are seeing a real change rather than an artifact of one measurement method. And this isn't something that suddenly appeared yesterday. The warning signs have been building for months. In June, Copernicus reported that global sea surface temperatures were already exceeding previous records for that time of year. By July, the global ocean had reached its warmest July on record. NOAA's July assessment found that global ocean temperature was about 1.02 degrees Celsius above its long-term average for the month. It was the first July in the NOAA record with a global ocean temperature departure above 1 degree Celsius. Then the daily measurements continued climbing. By the end of July, the global extrapolar ocean was already approaching the previous all-time daily record. And now that record has been surpassed. That progression is what scientists are watching. Not one isolated hot day. A pattern. The ocean has remained unusually warm, and the current trajectory has pushed it into territory that was previously reached during a different part of the year. But there is something else we need to understand. The number 21.1 degrees Celsius does not mean every ocean on Earth is 21.1 degrees. The global average combines enormous areas with completely different temperatures. Tropical waters can be extremely warm, polar waters can be near freezing, some regions are much hotter than average, others can still be cooler. The record is the global average across the extrapolar ocean. That distinction is important, but it doesn't make the record less significant. In fact, global averages can hide some of the most extreme regional changes, because while the planet-wide number is extraordinary, individual ocean regions can be experiencing much more intense warming. And that brings us to one of the biggest consequences: marine heat waves. A marine heat wave is essentially an extended period when ocean temperatures are unusually high for a particular region and time of year. These events can be devastating for marine ecosystems. Imagine living in an environment where the temperature changes only slightly. Then suddenly, the water around you becomes several degrees warmer than what your species normally experiences. You cannot simply turn on an air conditioner. You cannot move your entire habitat overnight. Some organisms can migrate, some can adapt, others cannot. Coral reefs are particularly vulnerable. Corals live in a narrow range of environmental conditions. When water becomes unusually warm for long enough, corals can become stressed and expel the microscopic algae that live inside their tissues. That process is known as coral bleaching. If stressful temperatures continue for too long, bleaching can lead to coral death, and the consequences extend beyond the coral itself. Coral reefs are ecosystems. They provide shelter and feeding grounds for enormous numbers of marine organisms. So when heat damages the reef, the effects can spread through the food web. Fish populations can be affected. Fisheries can be affected. Coastal economies can be affected. And communities that depend on marine ecosystems can eventually feel the consequences. But coral is only part of the story. Warmer water can also change where fish live. Many marine species follow temperature ranges. As ocean regions warm, some species move toward cooler waters. That can create strange changes in where fish are found. A species that was once common in one region may become less common. Another species may suddenly appear where it was rarely seen before. For commercial fisheries, that can become a major challenge. Fishing communities depend on knowing where target species are located. When the ocean changes, the map changes with it. And then there's another effect that most people never think about. The ocean helps regulate the atmosphere. Water is constantly evaporating from the surface. When the ocean becomes warmer, evaporation can increase. That puts more heat and moisture into the atmosphere. And moisture is fuel for weather. This does not mean that every warm ocean automatically produces a hurricane or a giant storm. Weather is far more complicated than that. But warmer oceans can provide additional energy and moisture to atmospheric systems. Under the right conditions, that can contribute to heavier rainfall and stronger storms. This is one reason scientists pay so much attention to ocean temperatures before major weather events. The atmosphere is interacting with the ocean continuously. The boundary between them is not a wall, it is an exchange. Heat moves upward, water evaporates. Moisture enters the atmosphere, winds push heat around, storms transfer energy. And the ocean absorbs energy again. It is a gigantic planetary feedback system. Now consider what happens when the starting temperature is already unusually high. A storm moving across a warm ocean has access to more heat and moisture. That does not guarantee that the storm becomes extreme. Other conditions still matter. Wind shear matters. Atmospheric pressure matters. The storm's structure matters. Its location matters. But the ocean provides part of the energy. And when that energy source is unusually warm, scientists pay attention. There's another consequence that happens even without a storm. Sea level. When seawater warms, it expands. This is called thermal expansion. It is one of the physical reasons sea level rises as the climate warms. The effect is not dramatic from one hot day, but across enormous volumes of ocean water, persistent warming adds up. And when warmer water combines with melting land ice, the contribution to rising sea levels becomes more significant. That matters because billions of people live near coastlines. A few centimeters may not sound dramatic, but coastal flooding does not require a massive rise in sea level to become more frequent. High tides can reach farther inland. Storm surge can start from a higher baseline, and places that previously flooded only during unusual events can experience flooding more often. So the ocean temperature record is connected to the coast in ways that may not be immediately obvious. But there is an even deeper question. Where exactly is all this heat going? Because the ocean is not warming only at the surface. The ocean has depth. A tremendous amount of heat can be stored beneath the surface. Scientists measure ocean heat content at different depths because surface temperature alone does not tell the whole story. You can imagine the ocean like a massive storage system. The surface is what satellites can see most easily, but below it is an enormous volume of water capable of absorbing and storing energy. That is why ocean heat content is such an important climate measurement. A short-lived surface temperature spike is one thing. A sustained increase in the heat stored throughout the upper ocean is something much larger. And the long-term measurements show that the ocean has continued accumulating heat. NOAA's ocean heat content records show continued warming of the upper ocean over recent decades. This matters because the ocean acts like a giant buffer for Earth's climate system. It absorbs much of the excess heat associated with human-caused greenhouse gas emissions. That has slowed the rate at which the atmosphere itself warms compared with what would happen if all that energy remained in the air. But there is a trade-off. The heat does not simply disappear. It goes into the ocean. And the ocean is now carrying an enormous amount of stored energy. That is why ocean warming is sometimes described as one of the clearest indicators of the planet's changing energy balance. Air temperatures can jump around from year to year. A cold winter can temporarily push temperatures down in one region. A volcanic eruption can influence global temperatures. Weather patterns can move heat around. But the ocean integrates changes over much longer periods. It remembers. And that makes the latest record particularly interesting, because this isn't happening in isolation. Global temperatures have also been exceptionally high. NOAA reports that July 2026 tied with 2024 as the warmest July globally. The ocean reached its highest July temperature on record, and El Nino is now developing in the tropical Pacific. So several major pieces are lining up at the same time. A warm global climate background, an unusually warm ocean, and a developing El Nino. The question now becomes, what happens next? The answer is not one simple disaster. There is no scientific basis for saying that this record guarantees some enormous global catastrophe in the next few weeks. That would be misleading. Instead, the concern is about probabilities and accumulating effects. If ocean temperatures remain unusually high, marine heat waves can become more likely or persist longer. Marine ecosystems can remain under stress. Warm water can continue contributing energy and moisture to the atmosphere. Coastal flooding risks can be affected by higher sea levels, and the developing El Nino can alter weather patterns around the world. Scientists will therefore be watching several things very closely. First, they will watch whether the record ocean temperature is temporary or persistent. Copernicus has specifically emphasized that continued monitoring is needed to determine whether the latest record represents a short-lived exceedance or conditions that remain elevated. Second, they will watch El Nino. If El Nino continues strengthening, it could add another source of warmth to the climate system. Third, they will watch marine heat waves. Where are they forming? How intense are they? How long do they last? And which ecosystems are being affected? Fourth, they will watch the atmosphere, because the ocean and atmosphere are connected. Changes in ocean temperature can influence evaporation, rainfall, and atmospheric circulation. And atmospheric changes can then feed back into the ocean. This is why the next few months are so important. The record itself is already significant, but the trend after the record may tell us even more. Does the temperature fall back quickly? Does it remain near record levels? Does another record follow? Or does the strengthening El Nino push the system even higher? Those are the questions scientists cannot answer with certainty yet, but they can watch. And that is exactly what they are doing. Satellites are scanning the ocean. Buoys are measuring temperatures. Ships are collecting observations. Ocean models are tracking currents. Climate models are projecting possible future conditions. Every new measurement helps scientists understand whether this is a brief peak or part of something larger. And there is one detail about this story that I think is easy to miss. The ocean can look completely normal from the surface. You can stand on a beach and see blue water, waves, sunlight, clouds, maybe a few boats on the horizon. Nothing about the scene tells you that the global average ocean temperature has just crossed a record. There is no warning siren, no giant crack in the water, no visible line separating normal ocean from unusually warm ocean. The change is mostly invisible. But beneath that ordinary surface is a planetary system carrying an enormous amount of energy. And that is what makes ocean science so important. The biggest changes on Earth are not always the most dramatic things we can see. Sometimes they are changes in temperature measured across millions of square kilometers, changes in currents, changes beneath the surface, changes in the chemistry of seawater, changes in ecosystems. And slowly, those invisible changes can begin showing up in the world above. That is what scientists are watching now. Not one isolated temperature reading, an entire ocean system. The latest Copernicus measurement is a record. The July NOAA data shows that the monthly ocean temperature was also at a record high for July. And the developing El Nino gives scientists another reason to watch the coming months closely. So this story is not finished. In fact, the record may be the beginning of the most interesting part. Because the question is no longer whether the ocean can reach an extraordinary temperature. We now know it can. The question is how long these conditions last, where the heat moves, how marine ecosystems respond, how the atmosphere responds, and what happens when all of these systems interact. The ocean covers most of our planet. It controls enormous parts of Earth's climate. It absorbs heat. It moves energy around the globe. It feeds storms. It supports ecosystems. It stores carbon. And it helps regulate the conditions that make human civilization possible. So when the ocean changes, eventually we notice. Maybe through rainfall, maybe through storms, maybe through fisheries, maybe through coral reefs, maybe through coastal flooding, or maybe through another temperature record that scientists did not expect to see so soon. Right now, we don't know exactly which of those signals will become most important, but we do know something unusual has happened. On August 22nd, the global average sea surface temperature outside the polar regions reached about 21.1 degrees Celsius. That narrowly broke the previous daily record from March 2024. And it happened during a time of year when global ocean temperatures would normally be moving away from their annual maximum. That is why scientists are watching. And that is why the next few months could tell us much more than this single record ever could. Because the real story isn't simply that the ocean is hot. The real story is that Earth's largest heat reservoir is changing, and the rest of the planet is connected to it. If you want to keep following the biggest changes scientists are detecting across Earth's oceans, atmosphere, geology, and climate, subscribe to WideView. We will keep watching the data as it develops, rather than waiting until the consequences are impossible to ignore. Because sometimes the biggest warning isn't something you can see. Sometimes it's a number appearing on a scientific monitor, and right now one of those numbers just broke a record.